Hello everyone. My name is Vivek Pandey. These days, for past 1 month or so, I have been spending a lot of time creating a chess engine, and I am finding it sort of addictive to try to create chess engines which can play better and better quality chess. And this series of videos, this particular is part one of I don't know how many videos I will be creating. So this series of videos is documenting my journey of creating hopefully very powerful chess engine. By the end of this video, you will be creating, if you follow along with me, a chess engine whose ELO rating is around 1300. So not exactly a beginner. It can play a decent chess, but maybe still one level away from being a moderate club level chess player, and a long way away from being a grandmaster level play, providing a grandmaster level play or something. So here is the outline of this particular video. First, we will talk about why do I want to create yet another chess engine. There are a lot of very strong chess engines. If you follow the chess engines, you would be knowing about Stockfish and Houdini and Leela Chess Zero and maybe Alpha Zero. So why do I want to create another chess engine? We will talk about that. Then we will talk about basics of creating chess engine, and then thirdly we will actually create a chess engine. We will do a lot of vibe coding to create that, and you will find that as a result of these LLM assisted coding, creating a chess engine, the writing the code part would be quite straightforward once we know the basic ideas. And we will be using that code, we will be training our chess engine, and finally we will analyze the engine that we have created. We will make it play against some stockfish, weaker level of a stockfish. We will look at its moves, where is it strong, where is it weak, and we will see, we will try to find its elo strength. So these are the four things that we will do: motivation, basics, actually doing it, and analyzing what we have done. So why do I want to create chess engine to begin with? So the thing is that so the first thing that we talk about is why do I want to create a chess engine to begin with, and following are the reasons of why I'm taking this expedition. The first one is actually the most important reason. Lately, some months ago, I got very interested in understanding how AI is helping us do theorem proving in mathematics. If you are following the news, you would be knowing that AI is helping prove more and more sophisticated theorems in mathematics. For example, alpha proof in the actually not in 2024 but in 2025 IMO, it produced a gold level gold medal winning performance. So as I slightly deep dive into this topic, I figured out that there are some languages like Lean, which is a functional programming language, in which we can rigorously and formally write the statements of mathematics. We can specify the axioms, we can specify the theorems, and we can write down the proofs in Lean, and then the Lean compiler can verify that our proof is correct. Uh, and so I got interested in this topic, and then I read the alpha proof paper. And alpha proof, I figured out that it is based on deep reinforcement learning. Reinforcement learning, where there is a neural network also involved in this, in the process. So let me just take you for a moment to the alpha proof paper. Yeah, this is the alpha proof paper by Google DeepMind. Alpha proof is inspired from Alpha Zero. We will soon talk about it. And it uses reinforcement learning. So I got very interested in studying reinforcement learning with the view of understanding how theorem proving can be done using AI. And so I also figured out that writing chess engine is a very good way to learn deep reinforcement learning. So while I wanted to do maths, doing chess is a easier, more gentler introduction to the whole field, because chess is simpler than maths. Why is chess simpler than maths? Chess is quite a complex game. However, at each point, any player has like 20, 30, 40 possibilities, while in maths, from any given state of affairs, you can go to infinitely new state of affairs. You can always say, if you're solving a geometry problem, for instance, you can always say draw the midpoint of this triangle, or draw this perpendicular to this side, or draw some circumcenter, or circumcircle of certain triangles. So you can do lot and lot of constructions. Let y equal to t square plus t, and then you can carry on, do something with y. So in chess, branching is like finite, but in maths, branching is infinite. So maths is more complex than chess. So using reinforcement learning, I want to understand. So by solving chess, I want to understand reinforcement learning. So that is the first motivation. Second motivation is that as I have been studying neural networks, I have some ideas about architectures, that maybe certain neural network architecture is better. Now, I cannot solve very, very complex problems using neural networks, or rather, I need some problem on which I can try out these ideas. And so chess engine would provide that background set of problem, that background problem on which I can try out my ideas. And lastly, it's just something exciting, creating a world-class chess engine with a limited compute budget that I have. I have to spend my personal money in renting the GPUs for training. So creating a world-class chess engine with limited compute budget should be exciting. And so these are the reasons why I want to create chess engine. Maybe some of them resonate with you. All right. So now that we have covered the first part, why I want to create chess engine, let's go on to the second part, where we talk about basics of creating a chess engine. So to understand the basics of creating a chess engine, for the moment, for some time, let's assume that we have a lot more compute, effectively infinite compute and infinite memory. In that case, we can just solve chess. After all, chess is a finite game. The number of positions in chess is finite. It's very large, but it's finite, and number of possible games is also finite. So in principle, we can solve chess, and we will soon see that solution, and that solution then will inspire reinforcement learning as well, because practically we don't have infinite computer memory. So for now we are saying that we have lot and lot of compute and lot of memory, and in that case we solve chess using dynamic programming technique. If you have done undergrad computer science algorithms course and you have paid attention in that course, then you will be knowing about dynamic programming. And if not, no problem. The video is such that we will implement the solution without referring to the without saying that we will implement the solution from the first principles. So let us spend some time how we would solve in that case, how we'll solve chess in that case. And the first question that comes is, what is even meant by solving chess? And by solving chess, we mean that for any given position, you should know two things. One is its eval and the other is its policy. And we will see that these terms will make a reappearance when we study reinforcement learning. So eval, meaning eval is short of evaluation, which means that with a perfect play, is it a win for white, is it a win for black, or is it a draw? What is the evaluation of this position with the perfect play? That is the meaning of eval, and we want to know the eval of any given position, who is winning. And policy means what is the optimal move for the side whose move it is. Huh? So in particular, what we mean is that if it is white's move and the eval of the position is white, then the move after the move, the new position, its eval should also be white. If it is white winning, then if the optimal move for white is such a move that after that move also white is winning. Huh? And if eval is draw, huh? And then the optimal move is a move which keeps it draw, huh? Because even if the eval is draw and it's white's move, white may make a silly move and the evaluation of the next position may become winning for black. We don't want that. So this is the meaning of policy, huh? The optimal move, huh? Quite intuitive. And identically, symmetrically, if it is black's move, then we want that the move should keep the black win, and if the eval is draw, then it should keep it a draw. So solving chess means we should be knowing these two functions. We should be able to write a function in some programming language which, given the position, we should be knowing the eval, given the position, we should be knowing the policy, and if we know these two things, then we have solved chess. Now we will see how to solve chess using dynamic programming. And the way to solve chess is this. Actually, it's a way to solve any finite game. First, let's make a list of all the positions that are reachable in chess. There are many ways using which you can enumerate all the positions which are reachable in chess. Let's not go into how you will do that, but you have a position, you have a list of positions which are reachable in chess, and the number of such positions in chess is like 10 power 50. Our assumption is that our computer has way more memory than what it actually has today. So these are the positions. Maybe this is position number 1, the starting position. Maybe this is position number 2, 3, and so on. So there are lots and lots of positions. We enumerate all those positions. We make a list of all those positions. Now, there will be this slide is related to the base case of dynamic programming, where the recursion has ended. In some positions, one side is already checkmated. For example, in the first position, black is checkmated. In the second, also black is checkmated. The first position is the famous scholar's mate. The second is the back rank mate. In this third position, it is white which is checkmated. And if you know chess, this is known as smothered mate. In the last position, also white is checkmated. So for out of those 10 power 50 positions that you have enumerated, in some positions the game has already finished, one side is checkmated, and in that case the eval is white or black. We define the eval to be either W or B. W if white has won, and black if B has won. And in that scenario, we can take policy function to be null. Now there is no move to be made, so asking the question as to what is the best move in this position is nonsensical. So we output the policy function as null. So for now, for some of the positions out of those 10 power 50 positions, we know our eval and we know our policy function. Okay, there is one more case in which we know the eval, where we know that the game position is drawn. If there are only 2 kings, we know that now nobody will be able to checkmate the other side. Similarly, if there is just a king versus king and bishop, these we know that now even with very poor moves, the game is drawn. No side can even blunder the game and award a victory to the other side. So in these positions, we say that eval is D, that the game is drawn, and the policy function can output any valid move. There is no way to win, there is no way to lose. So we know this is the base case of the dynamic programming. For some of the positions, we know what is the eval and what is the policy. Now we consider the single step of the recurrence of dynamic programming. So we have a lot of positions that we want to solve. We have already solved some of those positions, and in one step of recurrence we will expand this set of solved positions by a little bit. So let's see how it goes. All the unsolved positions that we have, let's divide them in two parts. A part where it is white to move and the part where it is black to move. And this solution is for the part where it is white to move. A black to move part is analogous. So now, and let's take one unsolved position, pos, where it is white to move. There are two scenarios in which we can tell what is the eval and policy for pos. Scenario one is this, that if m1, m2, mk are the possible moves from this position pos, which we are trying to solve, a single position pos, we are looking at all the positions which are unsolved and it's white to move and trying to solve them. And one position that we are looking at is known as pos, and m1, m2, mk are the moves possible from pos. If one of those moves is such that the eval of the resulting position after the move is white, that means we know that if I make the move mi, then the resulting position is already solved and white is winning in that case. Then I can say that even the eval of pos is w, because I can always make that move. And I can also say that policy of pos is mi. Mi is the right move. So in this scenario, I can solve for pos. I can find the eval and policy for pos. I can solve pos. Another scenario in which I can solve pos is if I know the eval of all the positions that can be reached in one move from the current position, then eval of current position will be the best of these evals that I can reach. So clearly, so I know the evals of all the next positions. Clearly, none of them is going to be W, because if any one of them were W, then we would have gotten into case 1 and it was solved. So it means that these next positions are, we know the evals of all of them. So they are either, the evals are either D, that is draw, or B, that is black is winning. If in all of those evals, if all of those evals are D, that is draw, I'm sorry, if some evals are draw and some evals are black, then eval of my position is also draw, because I will take that drawish path. Why will I take the path where it is black to win? But if the next positions are all having eval W, so all the subsequent positions have victory for black, then any move I make, I am going to lose. So the eval of this position is also B. So in these, however, if eval of not all the next position eval to move, and not all the next positions eval is known to us, so we don't fall in case 1, we don't fall in case 2, then we say that fine, we will leave this eval as unsolved for now. So in one step of a recurrence, we solve some more positions. Similarly, we solve some more positions where black is to move. So this is one step of recurrence. And what we will do is, we will just run this recurrence step 1000 times. And an assumption is that all the positions which are reachable will be reachable within 1000 moves. Typical chess games are anywhere between 20 moves to, I don't know, maybe the longest game ever is like 200 moves or something. So yeah, this is slightly not rigorous, but we are just getting an idea of how to solve chess using dynamic programming, not trying to be fully airtight here. Yeah, so this way we can solve chess. Yeah, and there are some other rules that we have not considered. There is a 50 move draw rule which we have not thought about. So but we can always give, with this fundamental idea, we can always take into account those nuances. So in this DP exposition of solving chess, we have understood about eval function and policy function. All right. However, we now move on to the more realistic scenario. We don't have infinite compute or infinite memory. So, what we do is we try to program an engine like the way humans think. So, let us. So humans also have a policy function and eval function. Let us see what they look like. When we play chess, we intuitively know which 2 3 moves are the best moves to play. Huh? And in reinforcement learning lingo, this is known as policy function. Huh? So in the DP world, we were saying that policy function is one move, the best move. But in RL world, the policy function is the probability of moves. Huh? It says that M1 is best move with 40%, M2 is best move with 30%, and so on. Huh? And nextly, we also have a sense of how good a position is without even considering any moves from that position. Huh? We can just look at a position and say, hey, this is having a lot of material, this is having less material, so this move is winning. Huh? We can always we have such judgments also, and that is known as value function. So we don't explore the game tree, we just look at the position and try to understand, try to quantify how good a position is, and that function is known as value function. It is a number between -1 and +1. Huh? So -1 means black is winning, +1 means white is winning, 0 means I think it is equal. Huh? So value function also becomes in our DP exposition, the value function only had 3 possibilities: +1, 0, and -1. Huh? W, D, and B. But now it is a continuous, it is a real number between -1 and +1. And what will happen is, we will see in this video and subsequent videos, is that we will learn both policy and eval functions using neural networks. Okay, so the standard reinforcement learning, the way AlphaZero or Leela Chess Zero go about, is using something known as Monte Carlo tree search, but that is a little bit advanced for the for doing as a first thing. So we will not look at MCTS right now. And rather we will only implement the value function. We will soon come to it, but let us have a quick summary of existing chess engines. So there is Stockfish. So these are some of the chess engines which are available as of now. As you can see, their rating is anywhere between 3600 to 4000. For the sake of completeness, best human is like at 2840. This is Magnus Carlsen. Gukesh, the world chess champion, is at like 2750. So best humans are at like 2800, 2900 rating. And best chess engines are at 3600 to 4000. We will see by the end of this video, we will create a chess engine whose rating is like 1300, 1300, and in subsequent videos we will try to improve that rating. We will see. It is as of now unknown to me how far I can push. All right. And in this video, we will only implement the value function for simplicity. And then at the time of making the move, we will do something known as 3-ply search. We will look at, we will see what 3-ply search. 3-ply is like, I make a move, you make a move, I make a move, and I consider all such possibilities and figure out the best move for me. So we will look at it when we get there. So now let us start creating the real chess engine and train it. And here is our strategy about how we are going to do this. First, we will figure out a way to represent the board. So neural networks need some representation of the board. The board is normally consisting of lots of pieces laid on a 8x8 board. So how do we represent it as some array or as some tensor? This is what we will talk about. Then we will figure out a neural network architecture. Then we will get training data for our engine from Lichess. Then we will train the network and we will see how it performs against Stockfish. So here is our broad idea. we will have some representation of the board, and that representation of the board will be fed to the neural network, and neural network will evaluate somewhere between it will output a value between -1 and +1, which will tell the evaluation as per the neural network. And neural networks works with tensors, that is multidimensional arrays. So we need to find a tensor representation of the board. And I have read through the Leela Chess Zero documentation, and I have taken the inspiration from there about how to represent the chessboard. So if you go through somewhere in this document, you should be finding the so input format. So Leela Chess Zero has a much more complicated representation of the board, but I will use a much simpler representation of the board. Wait a minute, how to yeah, okay. So what we will do is that we will encode the board as a 18 cross 8 cross 8 tensor. So 8 cross 8 is the size of the board, as we all know, and we will have 18 8 cross 8 matrices. We call them 18 planes. And all of these 18 cross 8 cross 8 numbers will be either 0 or 1. Now we know that each side in chess has 6 types of pieces: king, queen, rook, knight, bishop, and pawn. So and since there are 2 sides, there are white and black, so there are overall 12 types of pieces, and we will have 12 planes for those 12 types of pieces. And so for example, there will be a plane for white rook, and so in that plane, on whichever squares white rooks are there is a white rook, we will have 1, otherwise we will have 0. For instance, in the starting position, we know that the rook is there on these 2 positions, on these 2 squares, so we will have these 2 squares as 1 and the rest of them as 0 for the initial game of for the initial position of the chess. This will be the these will be the values for the white rook plane. Similarly, the next figure shows the values of the value of the black bishop plane. There are 2 ones there. Similarly, there is a white pawn plane. These 8 squares are 1, the rest of them are 0. So there are these 12 planes. Then there is one plane for turn. We need to encode as to whose turn it is, and we will have all of the board, all of the squares as 1 if it is white's position. So look at this last diagram, and if it is black's move, then we will have all of it as 0. So this is our 13th plane. Then there are 4 planes for castling rights. So in chess there is castling. White may or may not castle on the king side, white will lose the castling right if the king has already moved or the king side rook has already moved. So if the white has the castling right, then the corresponding plane then the corresponding plane white king side castling right plane will all be consisting of 1s, otherwise it will consist of 0s. So there are 4 such planes: white's king side castling, white's queen side castling, black's king side castling, black's queen side castling. So there are these 4 planes, and then there is one plane for an n% pawn. If there is any pawn which is n%, that is, it has just now moved by 2 squares and there is an adjacent pawn to it of the other side. If you know the chess, then you will know what I'm talking about. So we will have one plane for denoting if there is an n% pawn. And in particular there will be a 1 corresponding to the n% pawn. In the initial chess position there is no n% pawn, and so all of these squares are 0. So there are a total of 12 plus 1 plus 4 plus 1 equal to 18, 12, 13, 17, 18. Yeah. So overall there are these 18 planes, and so our input consists of 18 cross 8 cross 8 booleans, you can say, but actually they are integers because they will soon be we will soon be performing floating point operations on them in the next steps. So they are all floating point numbers whose values happen to be either 0 or 1. So this is our input. Now let us see how our neural network looks like. This we will soon go through the neural network. This also I have taken from the Leela Chess Zero's documentation. So we are closely following their network architecture. Maybe in future videos we will try to innovate on them, but first we need to start from somewhere and take benefit of the wisdom of the wise people. So we will be except that their neural network is much wider and much deeper, but when I am doing my own studies, then I need a neural network of the size so that I can do some training within a reasonable amount of time on a single GPU. So that is why my neural networks are going to be much smaller, and we will be trying to innovate on the ideas side. Okay, so we take this initial chessboard and we form this input, which is 18 cross 8 cross 8 in size. Then we take it through a 3 cross 3 convolution layer followed by batch normalization, and we will have 256 channels. So if you know about neural networks, 3 cross 3 convolution layer is like a window, which is like a 3 cross 3 window which goes over the complete 8 cross 8 chessboard. So at a given point, this 3 cross 3 layer is focused on some 3 cross 3 area of the chessboard, and actually all 18 planes. So it considers 3 cross 3 cross 18 floating point numbers which are in its purview. It takes its some linear combination and adds some bias, and then that is its output. So there is a 3 cross 3 convolutional layer followed by the batch normalization. So there is one batch normalization for each of the 256 channels. So for each of the 256 channels, we will have some batch size, maybe batch size of 32. We will take the 32 cross 8 cross 8 numbers, find their mean, find their standard deviation, and for each sample x we will change it to x minus mu slash sigma. Okay, so so we will have a convolutional layer followed by the batch normalization layer followed by the activation function. We will use the most popular activation function value. Okay, so this is the initial processing of the input. Then we will have what is known as ResNet, and we will have 8 layers of ResNets. Each layer of ResNet corresponds to, it consists of 2 conv plus batch norm outputs, and so it consists of 2 layers of conv plus convolution, 3 cross 3 convolution plus batch norm, and at the end of the and to the output of the second convolution layer we add the input itself. So you see there is an arrow from the top to the bottom. We do this addition. So this is so that the initial signal also this is so that the later layers also have access to the original signal which was there. And so we have 7 such layers. We have 8 such layers. So there is the initial convolution in batch norm followed by the 8 layers of ResNets, followed by another convolution in batch norm, and there are potentially some dropout layers in the middle, In the end, there are some fully connected layers followed by and the final activation function is 10h, because 10h, the output of 10h is between -1 and +1, which is what we want, so very convenient for us. So finally we use 10h, and that outputs a number between -1 and +1, and that is the output of the neural network, and we train this neural network on some Lee-Chess data. To understand this slightly better, let's just have a quick look at what is the dimensionality of the various data flowing through our neural networks, and what are the weights involved. So input is, as we discussed earlier, 18 cross 8 cross 8, and then since there are after the 3 cross 3 convolution and batch normalization, since there are 256 channels, this input becomes 256 cross 8 cross 8. The ResNet layers don't change this dimensionality, and after all these ResNet layers also, the output is 256 cross 8, 256 cross 8 cross 8. Then after the okay, in the previous slide I said this is a con, but actually this is a 1 cross 1 convolution layer, which is used to downgrade the size of the data which is flowing through. So as a result of this 1 cross 1 convolution, the size of 256 cross 8 cross 8 reduces to 16 cross 8 cross 8. And then after this, as a result of the fully connected layer, it becomes a 256 layered output, 256 sized vector, and then finally there is a single scalar outputted, and whose value is between -1 and +1. I have also listed down the number of weights and the biases that we use. Very important. One important thing to note is that bulk of the weights are in these ResNets. So one layer of ResNet has around 1.2 million weights. So 8 ResNets have around 9.6 million weights, and the rest of the weights are relatively small in number, 41,000-ish for the initial layers, and then some 4,000 and a quarter million in one of the fully connected layers. So this is around overall around 10 to 11 million weight network, which we will be training. Before we can get to the coding part, there is one more detail that we need to know, and that is around Fen strings. So I have told you that our neural network will take as input board encoding, and the position encoding, which will be a 18 cross 8 cross 8 tensor, and we saw earlier for the format of this encoding. But this format is difficult to work with when we will be analyzing some positions manually, and it is a little difficult to store also unless you do some compression and all, and also non-ML people's chess players, or when we are recording chess games in some files, we use what is known as Fen strings, and we will be actually storing the positions in files in Fen string format, and it is only that when we have to give it to the neural network, then in runtime we will convert the Fen strings to the 18 cross 8 encode, 18 cross 8 cross 8 encoding. So it is important to understand what is Fen string, and it is quite a straightforward thing. So let's spend some time on it. This Fen stands for Forsyth-Edwards notation. This is the notation for describing board position in the chess game. And there is a nice site, Chess Fen Viewer. Let me make a few moves to be able to help you understand what is a Fen string. I will just make some random moves. Mm, yeah. So for this position which is on the board, this is the finestring. Uh, it's quite straightforward. There are some characters separated by slashes. Huh? A bunch of characters slash, a bunch of characters slash, and so on. Each bunch of characters correspond to a row. So there are these 8 bunches: one, two, three, four, five, six, seven, 8, huh? Because there are 8 rows. So the first row is R2Q, meaning first there is a black rook. Small r means black rook, uppercase R means white rook. So there is a black rook followed by 2 blank spaces. This is the 2, followed by a queen, a king, a bishop, queen, a king, a bishop. Then there is a 1 blank space, empty square, and then a rook, and so on. Let's look at, for example, the seventh row. Seventh row is this PP3 PPP. PP, the 2 pawns, 3 meaning 3 blank squares, and then again 3 pawns. So, so this is the description of the position. Then there is some more description. W means that it is white to move. For instance, now if I make a white move, then this turns to B because it's now black to move. KQ means it is a description of the 4 castling rights. Uppercase key means white king castling rights are intact. Upper Q means queen side castling right is intact. It cannot castle right away, but it can castle in the future because the king or the corresponding rook have not yet moved. Similarly, the castling rights of black. Then dash is, I think it is the description of the in peasant pawn, if any present. And 0 and 1, these things actually don't matter. They mean how many moves have been made. Right now, even if we are making the move, it is not increasing, but in real games, because we are just putting one position, in real games, it increases as you make the moves. But for the purpose of for our purpose, this is immaterial. So coming back to the presentation, uh, yeah, so this is the fenestring that we will need to that we have to understand. And now let us straight away go to real coding. Let's do vibe coding, and yeah, give me a minute, we have to get started. Where is it, just a minute. Yes. Yeah, so right now this is an empty directory. Vivek Pandey chess attempt 1, huh? And whatever code I am writing, actually Claude will write the code, not me, but whatever code we write, I will put it in GitHub and you can take it and copy it. But if you follow, actually you will see that you can write your own code very quickly. Okay, so on the left side I will have Claude, and on the right side we will view the files that Claude creates. So let me provide some instructions to Claude. I want to create a chess engine. For encoding the board, I want to have 18 planes. Okay, let me rather say to it that I want to create a neural network based chess engine. We will train it on evals got from leeches. So what we will do is that we will, after creating some files here, we will go to leeches, we will download a bunch of games. We will download the leeches. Leeches uses Stockfish. So we will download the Stockfish evals of millions of positions from leeches, and that is what we will use to train our neural network. Okay, so I want to create a neural network based chess engine. We will train it on evals got from leeches. For encoding the board, I want to have 18 planes, 12 planes for the pieces, 4 for castling rights, one for whose move it is, and one for en passant. The neural network will be trained for eval only, or rather let me call it for value head only, not policy head. We don't want, so remember, okay, I have not discussed this earlier, but we did talk that there is a policy function and there is a value function. Right now we are training the neural network for value function only. In some future video we will train it for policy function only. Actually, a side note is that initially when I was trying to make the engine, I was training it both for value engine and for policy engine, and then things were getting very complex, and I thought, okay, let me first do a good job just with value, and play the engine, and actually do a min max type of search, that 3-ply search, and rather than worrying about the policy head. So right now no policy head, so neural network will be trained for value head only. There will be a 3D, no, not 3D, but 2D conv plus batch, 2D conv with 512 channels. That's what we had decided. With 512 channels, there will be 2D conv followed by batch norm. There will then be 8 layers of resnets. Each, I think a resnet already implies what it will be. I mean, in our resnet there were 2 conv plus batch norm pairs within each resnet. I am hoping that Claude will understand that automatically. I don't need to specify. Then there will be 2 fully connected layers followed by tanh, which will output the eval between -1 and +1. Okay, write all the code encoding neural net training in one file only. I am writing it in one file because I will be actually training on a Databricks notebook, and in Databricks it is easier if I have just one big file rather than many files. Normally I would have liked to write a modular code, but given this constraint I want to write everything in one file only. You can create other files for testing purposes. The input data, the training data will consist of finstrings, comma eval pair, where the eval will be coming from Stockfish via leeches. Anything else would I like to specify? No, this sounds like good. We have told everything. Let us see what happens. We will look at the files, and if we want to change anything, we will change it. Let's see. It will take a little bit of time for everything to be generated. So while this is going, earlier I tried to do a MC Monte Carlo tree search, policy head, value head, everything in one go, and then nothing was working. And I was wondering whether nothing is working because there was some bug in my code, or just the training is too slow. Why, we don't know. Then I said that okay, forget about MCTS, that Monte Carlo tree search, forget about policy head, let's just train with value head. And initially I trained only mate in one positions. And when my program was able to, when my model was able to learn mate in one positions, that I got confidence that yeah, I am able to, my model is able to learn something. Then there were few iterations involved. I trained the model on mate in one plus normal chess playing positions. Then finally I moved to just pure no mate in one, no specific mate in one positions, but just the positions that we get from the games. Okay, so let us see. Do I want to create a chess engine? Yes. Let us see how it goes. I will turn off this whole video thing, and I will be back when this guy is actually done. Okay, so we have now the code written by Claude. Let's look at the code. It has produced two files, chessengine.py and testchessengine.py. Let's have a quick look at chessengine.py. Firstly, let's see that yeah, there is the encoding of the board, and there is this fen2 tensor. It will take a fen string and convert into a 18 plane tensor representation. This is what we had asked Claude to do. It has also written a function around normalizing and denormalizing the eval. The thing is that Stockfish evals are, I think, between -1000 and +1000, but our evals are between -1 and +1. So you need to normalize and denormalize the evals. I'm sure it must be using it somewhere later. Okay. Let's have a look at the residual block. Let's have a look at the overall network. Let me open up the diagram. So there had to be initially a 3 cross 3 convolution, followed by batch normalization, followed by the ResNet layers. So there is indeed a 3 cross 3 convolution, followed by the batch norm, followed by the set of ResNet blocks. And there are 8 ResNet blocks as we had requested Claude. Finally, there is a there is again a convolution and batch norm. This is this one. This is a kernel size 1. Yeah, so this is a 1 cross 1 convolution. And then there is followed by two fully connected layers. We wanted first fully connected layer to go from size 16 to size 256. It is I'm not sure yeah, it is indeed going to size 256, but the input seems to be of size 32 here rather than 16. Okay, okay. So this conv layer is outputting 32 channels rather than 16. We will live with this. Yeah. Claude has made some reasonable assumptions. We did not exactly specify the parameter, so it has taken some reasonable assumptions. Okay, then we it is doing something related to data set. It's asking, it's saying that it will load the data from the file. We were not very clear to Claude about how we will do this. So now what we will do is we will now prepare the data. So we have let's go to the slides and look at our overall plan. We figured out a way to represent the board. We have devised the neural network architecture also. Our training script is ready, close to ready. Now we will get the training data from leeches. That is the very, very important thing. We are using leeches as the source of truth. I mean, not leeches, but really Stockfish engine, whose evals are available in leeches. We are using that as source of truth for now. Maybe our secret dream is that we will be able to defeat Stockfish at some point of time, using Stockfish as our guru to begin with. So next thing is to get the training data from leeches. So now we will get some training data from leeches. Let's search for leeches game database. Yeah. So Leeches provides us with games of database that contains millions of games. Actually, it has some 7 billion standard rated games, huh? And for many of these games, as we download the file and look at its content, we will see for many of the games, Leeches provides the Stockfish eval for each position that has been encountered in the game, and those evals is what we will take. So there are some 30 gigabyte files. I would like a smaller file because I won't be training on a lot of data. So let's look at maybe this file. Maybe I can go even smaller. 3.8 GB, yeah, 12 million games. I don't need. I will be training on some 4 million positions, and 4 million positions I can get from maybe like 400,000 games. Uh, but I will also not take very, very highly rated games because my engine is not very strong, so it will benefit more from slightly weaker games, not really grandmaster level games. So 400,000 for 4 million positions, I need 400,000 games. For 400,000 moderate level games, maybe I need 4 million games. So 4 million games I can get very easily from one of the simpler files. So let's take this file. Let's download this March 2016 file. It will take, yeah, it looks like it will be done very soon. 8 minutes left. I will maybe pause the video and I will be back after a few minutes. So the download has finished. We downloaded this some uh, gigabyte file. We will now. I want to show you its contents. Leeches DB standard. Yeah, this is the file we downloaded. So yes, ZSTD. I will decompress this file. Let's decompress it. A gigabyte of file should expand to maybe 10 gigabytes at most. No, it's less than that. So we have this file. This is a 5 gigabyte file. Let's look at its contents. Is 5 gigabyte too much to load into Vim? Maybe it is too much. We will just wait. Yeah, my RAM is like 8 GB. This Mac is like 8 GB. So maybe I have done a mistake. What we will do is we will, okay, fine, it has loaded only, fine. Okay, yeah. So we have lots and lots of games here, huh? As that file said, we have 5.8 million games in this file. So this is, for example, one game, 1d4 c5 something 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 something. Okay, so the games are there, but that doesn't really help us. Yeah, some people played some game. How do I know whether the game was good or game was bad, or but in particular we want to know the eval of each position that was encountered in the game. And in some of the games eval is also given. So I just searched for eval. So for instance, in this game, after 1d4 the eval according to Stockfish was 0.19, and eval according to Stockfish after 1 dot d5 was 0.17, and so on. And towards the end, if you see, the eval is by 20th move, just a minute, yeah. So you see, eval is like 20.07, very high eval. It means black is white is winning. And towards the end we start getting like hash 6 or hash 11, means it's mate in 6, mate in 11, those sort of things. Okay, so there are a lot of positions like this which are available to us. So now what we will ask is, we will ask Claude to look at these, look at the games where eval information is present. Or maybe I can myself filter out the games where eval information is present. Let's see for how many games eval information is present. Just a minute. This is a big file, and now my Vim is not working properly. I'll just kill this. 75915. All right. Okay. Now there is some problem. Just a minute. All right. Now I'm back, and there is this additional file which is gotten created. I will delete this file, and this is my original file, or is it? It was a slightly bigger file. Let me not take chances and just delete this one and regenerate it from the original file. Let me have the Claude window around here. Okay, so what I will do is this grep eval wc minus l. This will tell me how many games there are which have eval information. It's taking a bit of time. So my idea is that I will generate, yeah, okay. So there are around 800,000 games which have this eval information. So what I will do is this. I will ask Claude to do all the work. Look at the file. What was my file name? This one. -03.pgn. Some games have eval information in them. Look for the lines containing the string. Actually, maybe let me do it slightly differently. I will just grep for eval and write those games in a separate file. So I will, so for instance, let me just see the first thing. Yeah, so there is this one game. There is similarly, there are now two games. So what I will do is I will just say games with eval dot pgn. So now games with evals.pgn will contain only those games which have evals. So now I will see, look at the file games with evals.pgn. It each line of this file contains a chess game along with evals on each position. From this file, create a new file, training database dot csv with two columns, fen string and b is stockfish eval. Yeah, for each position encountered in each of the games. Note that some evals are like hash 1 or hash 2 signifying mate in 1 or mate in 2, etc. For such cases, put eval as plus 1000 or is it 100? I forget. Maybe 100, plus 100 or minus 100. Let's see what it okay, actually I should have written that please write a Python program which does this. So let us see if Claude does what we want. I expect it to generate games with evals.pgn, games with evals.pgn. Yeah, that file is there. Okay, so it's reading. The file is 1.2 gigabyte. Okay, it will create a Python script to parse and generate the training data CSV. Let's see what it does. Pip install chess. I thought that chess was already installed. Python chess. I think it is there, but okay, fine. I'll just go ahead with what it says. So now we are close to getting the data that we need. Well, not really close. So the idea is this, that right, so there are these 800,000 games, and assuming that each game will give us maybe like 100 positions to evaluate. So 800,000, 80 million positions we will get, and then we will figure out the histograms of the evals, because we would like our most positions in chess are evenly distributed. I mean their eval is close to 0, but we don't want all the evals to be close to 0 in our training, in our training. So we will choose position so that each eval value range gets equal representation in the training data. So we have to do a little bit of work to generate a good training data. Oh, it is running as well. Okay, I thought that I will run it. I wanted to see. Let's have a look at it. What it is put create training data. Uh, okay, yeah, it's quite smart. Yeah, I'm sure it would have done a good job here. It's saying I am creating. Yeah, so let's have a look at this CSV. Oh, right now there is nothing. It wants yes. I'm not sure what it is doing currently, what Claude is doing currently. I have done this with Claude earlier, so I know that Claude has enough know how to do all this. But right now it seems to be confused. Extraction returns nothing. Let me debug the issue more. So it is right now a little bit confused. Let's hope that it makes progress. It has found some bug and all. Sure, we don't have any problem with whatever you do. It is not that some production code will be impacted because of your mistake. Create training data dot. All of these things, doing them by hand would have taken a lot of time, and now I am able to do it in this live video. Hmm. It would clearly have taken me like a day or maybe maybe several days to do all this work, um, which I'm doing in a few minutes now with the help of the great LLMs. Oh, it's running the script. So now let us see if it. Okay, great. We are getting something. Yeah, indeed, there is this fen string and then there is the eval. The eval though is in centipons, huh? So it's like 99 rather than in the units of pawns. I would have ideally liked it in pawns. And yeah, you see, uh, there is this game which is proceeding. Mm. Oh, and here it has become 100, which means it was those mate in one positions, may mate in few move, and then next game has started from this place. So actually, I should ask it that dude, don't. Yeah, this is counterintuitive that my eval is 2977, which is like 29 pawns, and then suddenly it becomes just. Uh, 100 29 pawns, say it becomes just a single pawn. Wait, so we will have to give it slightly some directions because there is confusion in unit. How can I escape to interrupt? Okay, fine, escape to interrupt. Hey, wait, it's not working, huh? The eval should be in the units of pawn, not centi pawn. I'll fix that. Yes, eval should stay as pawns, not as centipawns. Correct. Yes. Now my instruction that if it is mate in 1, mate in 2, then your eval should be 100 will make sense, because I meant 100 pawns, not like 100 centipawns, which is just a single pawn. Oh, it's running it again. Let's see this again. Let me open it using Vim. Yeah. So there is some game. Its starting position is like 0.19, which is fine. And then then white gains an advantage, and it goes till like 29 pawns or something. And so white is hugely winning, and then there is a mate clearly very winning position for white. So let's have a look at some position. Let's have a look at this fen. Huh? We will fen viewer. I use this to view chess positions. So set board from fen, and this is the fen. It's white to move. And what do you think? Who is winning? White has a queen extra, so clearly white is winning big time, big time. Great. So these evals are doing all right. Yeah, we just saw a position whose evaluation is highly in favor of white as outputted by our program, and manually also we can check that it is really heavily in favor of white. White is just killing it here. So now we will wait for some time. We will let this program run. I am sure it will finish in like maybe 10-20 minutes. I'll be back when it is done. Okay, it has finished now, and if we see, we have let's see how many lines are there in this training database.csv. There are close to 50 million training positions that we have got now. So we can train our neural network on these positions. However, there is one gocha that we mentioned earlier in the passing, and that is that we would like usually chess positions are for most part evenly balanced, so most evaluations are between -1 and +1, but for our training we would like a variety of evals to have roughly equal proportions. So first let's find out what is the distribution of evals in this file. So read training database.csv and find the number of positions with eval, and let's make these ranges: eval less than -10, between -10 to -5, between -5 and -3, between -3 and -1, between -1 and +1, between +1 and +3, between +3 and +5, between +5 and +10, and bigger than 10. Huh? So how many ranges are there? -10, say, less than -10, -10 to -5, -5 to -3, -3 to -1. So there are total 9 ranges. All right. So let's see. Let's give it some time. It will get it done. Since I restarted the Claude, it lost all the context, and so it has to now read the file again, try to get the context and everything. Yeah, but it's smart. Wow, it's using awk. Normally, I have always seen it using Python, but it is this time using awk to analyze the distributions. So, great. It's a 3 point something gigabyte file. So it's a 3.1 GB files, taking a little bit of time to get our distribution. I know most of the valuation should be between -1 and +1, but how many evals lie in the more extreme ranges, that will help us figure out how much total training data we can get, because that will be the limiting factor, the amount of data in the more extreme ranges like less than -10 or -10 to -5. Let me pause the video. I will be back when it is done. All right, this is done. So what we see is that, yeah, indeed, we always knew that bulk of the positions will lie close to zero in eval, but there is plenty of data everywhere, and we wanted to train our data. I know I want to train on roughly 4 million positions. There are these 9 ranges, so I will say I'll take 400,000 positions from each of the ranges for my training set, and 40,000 ranges from each of the positions from each of the ranges for my validation. And we indeed have more than plenty of the data, more than enough data to get that. So write a file to generate two files, training data.csv and test data.csv. uh, Training data.csv should contain 400,000 data points from each of the above 9 ranges, and test data.csv should contain 40,000 data points from each of the above 9 ranges. So now we are going to create this training data.csv and test data.csv. First, let us have Claude write down the generation file for us. Once again, I will be okay. It is close to getting done. When it gets done, I will be back. Okay, this was done. So we now have 363.6 million data points for training, and 360,000 data points for validation. And if you are worrying about this additional one, it is just the header of the CSV file. Okay, there is, before we can start the training, there is one more thing that I should point out, and that is that right now, when we ask Claude to write our training script, it will be tracking the training loss and validation loss. Let us have a quick look. Yeah, so chess engine, it is actually it's not printing anything. Towards the end, it is I don't know what it is printing towards the end, But what we will do is train model history equal to trainer dot train. Sorry, wait. Trainer dot train. Yeah, let's see what it is printing on each epoch. Yeah, so what it is printing every epoch is validation loss and validation training loss, validation loss, and some validation MAE, mean absolute error maybe. But there is one more thing that I would be very interested, and I have found this useful to track, and that is that for what fraction of data points is your valuation not more than one pawn away from the stockfish valuation. And that is also a metric that I would like to track. So what I will say is that change what is this file name, chess engine.py to output after every epoch within one accuracy, i.e. for what fraction of data points are stockfish eval and predicted eval within a distance of one from each other. All right, this will yeah, loss is pretty abstract, and this is a little bit more concrete, that okay, yeah, for these many cases I'm getting it almost right. It should soon be writing it. Let's wait for it. Okay, yeah, it always asks for permission. Yes, now it has outputted this within one accuracy. Mm, Great. So now what I will do is I will stop the video. I will now try to run it on Databricks, which is the system where I run, where I have a GPU, and I will then report back how it goes. All right, so I am back, and while I was not on the video, I did a few changes to the files away from this video, and let me describe to you those changes. First change was that while I intended my model to be around a 10 million parameter model, it what Claude outputted was like 35 million parameter model. Let me see if my conversation with Claude is still around. Yes, so it became like a sorry, I have lost that conversation. I cannot trace it completely. So it became like a big model, and what I found out was that while just a minute, yeah. While I intended these outputs to be 256 cross 8 cross 8, they were actually 512 cross 8 cross 8. So I asked Claude to downsize it, and now I have like 10 million parameter model. That is one change that I did. Then second change that I did, actually I ran it on Databricks, and and the performance was not good, and then I realized that I had forgotten to change the loss function. So what Claude coded up initially was a MS loss function was MSE, mean square error. Huh? So if the actual prediction is like point 0.3, if the prediction is like 0.3 and the truth value is like 0.5, then the loss value is 0.3 minus 0.5 whole square. So it's like 0.2 square, which is 0.04. And actually we do a by 2. That's the convention because of some reason. Let's not go into that. But that is not a good loss function. The reason is that when your ground truth evaluation is quite large, let's say that a position's eval is +7, then as long as you are outputting something large, your model gives something large, it is okay. +7 instead of +7 becoming +5 or +6 or +7 or +8, all the things are all right only. All of these evaluations are saying that white is hugely advantageous, and it doesn't matter really how advantageous white is. But magnitude wise, same error. So 0.5 versus 1.5 is a big deal. 7 versus 8 is not a big deal, but 0.5 versus 1.5 is a big deal. And then I read in the literature that in such cases we use something known as Huber loss. And Huber loss is a loss function which combines the squared loss, L2 loss, with L1 loss. So as long as the residual, which is predicted minus actual, as long as it is small than some threshold, we go with our MSE. But if it is bigger than our threshold, then we go with a linear loss. So that is the Huber loss. And I asked Claude to shift to Huber loss. Let me quickly show you the code. Training data dot sorry, not CSV, chess engine dot py. Yeah, so I have set the loss to smooth L1 loss, which is the PyTorch's nomenclature of for the Huber loss. So this is another one thing that I did. There was one more thing that I did. So first thing was to reduce the number of parameters. Second thing was to change to Huber loss. And third thing was that, our input data is Fen strings like this. And we need to convert them to those 18 planes. And what the Claude outputted code was doing was that in every epoch it was pick some positions that it want to train on, and then it would convert all of them to the board representation. So each board, so each Fen string, if it is used in training 10 times, then it will be converted to the board representation 10 times. So I asked Claude that why don't you just find all the board representation of all of them to begin with, and then just use it. So that made my training faster. A fourth thing, so how about I just write down the things that I did while I was away from the video. Things done while away from video. Yeah, let me just write them down. Wait. I want it. Where are you? Yes, here you are. And where is the bullet point thing? This is the bullet point thing. Yeah. One was reduce parameter size, then Huber loss, then pre-compute board representation, and finally increase batch size from 32. It initially outputted batch size as 32, And then gradually I changed it to like 2048. My GPU that I'm using is A10G. It is a 24 gigabyte memory GPU, and I figured that this is the batch size that I can still fit in this GPU. So, and I figured that if I can fit it, then my training will be faster if I have a bigger batch size. Actually, when I was doing it with 32, then it was taking a lot of time, and I figured that a higher batch size is helps me speed up the training and not really compromising on the training quality or anything. So that was another thing, increase batch size from 32 to 2048. I even tried 4096 and it worked. Is it yeah, I even tried 4096 and it seemed to be working, but it was not giving any speed up. So I just said I will go with 2048. And then I copy pasted this same file chessengine.py. You see, it starts from neural network chess engine and ends with if name is main, then call main. So I copied this thing whole here. I had to initially do some pip install in my Databricks, and then from this neural network chess engine to this whole thing. Okay, wait, I will take you through this. Yeah, so I ran it, and I ran it yesterday night, and it has been running for like 14 hours, 14 and a half hours. In the middle I had outputted some print statements just to ensure that how training was, just to make sure that training was actually happening. And let us see how the performance has been. It has been running for like 14 and a half hours. It's a 10 million parameter model, and let's look at the loss first. And let's look at the validation loss. So validation loss 0.19, 0.17, 0.07, and 0.06, 0.05, 0.06 and 0.05, and it 0.053. It has been it is 0.0508. It's going down gradually, some sort of stabilized at 0.05 levels. It even goes to 0.04 and 0.044, which is a new low in the validation loss. So training is happening. 0.043, so maybe and yeah, so 670 epochs have elapsed. It will run for max of 100 epochs. If for 5 consecutive epochs no progress is made, then it will terminate before 100 epochs. Another thing is to track for how many positions is our evaluation not more than one away from the Stockfish valuation. And this, it started from 22 and then soon went to like early 43s and 48 and 49, 50, and if we scroll down it is like 54 and something, 55. So it's like at 55. So it is still continuing to make progress. The loss is at all-time low. We are at 70 epochs. It's making more and more progress. So we will give it some more time, but we do have some model, or anytime we get the best model, we save the model in the S3 file. So these files are saved now. Happy New Year to yeah, I mean, when you watch the video, maybe it will no longer be Happy New Year. But anyway, this is January 1. What a great way to start the new year. Yeah. So what we will do now is that we will download one of these models, and we will play against the model. So let me do it in front of you live. Download. Yes, it's downloading. Shouldn't take a whole lot of time. Okay, it will take a minute or so. And while, okay, let's just wait. It doesn't hurt to wait just like half a minute. All right, 12, 11, 10. Yeah, that's like next thing to Elon Musk's rockets, I guess. Okay, so we have this thing. Now we go here. We do mv tilde slash download. What was the file name? Chess model. Chess model. Here we have downloaded it. I will just say escape. I was doing something. Yeah. Yeah. I have done the model training, and the trained model is chess model epoch 063.pt. Can you please write a Python program that sets up a 100 game match between this model and Stockfish skill level 0 with 1 second per move time given to Stockfish. Our model should do a 3-ply search, should do a complete 3-ply search, uh, to find its best move. Let's see how it goes. Let me also quickly tell you what is meant by 3-ply search. What it means is this, that let me just write down here 3-ply search. Let's say I am white. I have 10 possible moves, m1, m2 up till m10, and I need to choose the best move. Now against m1, black has, let's say, 10 possible moves. And let those moves be like k1, k2, k10. Now against k1, white also has 10 possible moves. Let's say r1, r2, r10. Now what we will do is that against k1, since white has 10 possible moves, we will I will find out the evaluation of the board after r1, r2, r10, and clearly I will choose the best. Okay, so against k1 there is some evaluation which is the so if black plays k1, then I will play one of these ri moves such that my evaluation is the best, and that, so we can assume that if black plays k1, white will play that move. And similarly I can find out white's best move against k2 and k10 and up till k10 and so on. So that way, now whichever moves, so now I know what is the evaluation of the board after k1, k2, k10, because I know what white will move. So I can say whatever, so I will figure out that, okay, so this will allow me to figure out as to what black will play if I play m1. Because black will play that move which is most advantageous for him. So this way I can figure out what is the goodness got from m1. Similarly I can get goodness from m2 and m10, and then I can choose amongst these moves. So this is like just doing 3-ply search. Maybe my description was a little bit too fast, but you can do it some Google search or LLM search on this and understand it better. Note that I would ideally like to do really deep search, but my computational resources are limited, so I cannot do that. And the in some future videos we will do something like pruning, that you don't need to consider really all the possibilities, you only need to consider some possibilities. You can prune the trees in the middle and so on. We will do those sophisticated things later on. Okay, This is saying something. Yeah, Stickfish level 0. Okay, one more thing I should tell you is that we will be giving Stockfish only 1 second per move, while we will be doing 3 ply search. So actually we will take a lot of time because we are doing something very, very inefficient. All right. So it has written and it has said python play match.py. Let's see how does it look like. Yeah, python play match.py, and we will start very soon. uh, Please save, please, yeah, another thing that I want is please save each game. Please save all the games in a file. uh, Flush the file, flush the output to the file after each move of the engine or Stockfish. I want to flush because maybe after only few moves or after few games I would just control C the program, and I would still like my file to contain whatever has been played till that time. It's getting quite exciting. The moment of truth is arriving. While our model is getting slightly better and better, but whatever best model we have, we will pit it against Stockfish level 0. Why Stockfish level 0? We will see. We will see later on. This is the weakest Stockfish level. I can, in my previous experiments, I saw that I can barely somehow hold against Stockfish 0. All right, it's doing something. Let's see. Awesome. Let's run this. I will need to slash my bin activate. Yeah, this is the Python environment where all the pip installs have been correctly done. Python 3 playmatch.py, and the game should start. It has also said that you can do a tail dash. I'll just do tail dash 1. Let's see if it's currently just loading the model here, and the game has started. 1d4 c6. Who is white? Neural net is white. We have white, Stockfish is black, and we have played a very reasonable looking move, 1d4. So it's quite interesting. We have not taught the model that 1d4 is a good move that you should play, but the model has figured this out. 1d4 c6 e4 e6. Not a very bad start, I would say. Now I will pause the video. I will let this game go through and tell you the result after some time. All right, I am back. In the intervening time, 4 games have finished between the neural net engine and Stockfish level 0. 5 games have finished. 3 games have been won. Oh, sorry. 5 games have been finished, and all 5 games have been won by the neural net only. So this is awesome. We have won all 5 games that we have played against Stockfish level 0. Maybe actually now we are better than Stockfish level 0. We should rather compete with Stockfish level 1. But so we will now do the following. First thing that we will do is we will just tell you what do we mean by against whom are we playing. What is this Stockfish level 0? Stockfish is such a great engine. How are we how are we defeating Stockfish 0? So a little bit of details I will provide you about Stockfish, the levels of Stockfish. Then we will look at just one representative game. Uh, and After that, what we will do is we will look at some positions here. Our evaluation is very very different from Stockfish evaluation. So here are what are the points of weaknesses of our engine. Okay, so three things. One is some details about Stockfish. Other is and just looking at one game and then analyzing the poor performance wherever poorness is happening of the engine. And so these three things, and then finally we will conclude. So first thing was what is stock? What are the Stockfish levels? So when this is ongoing, let me take up another screen. Yes. So when we Stockfish is a very very prominent open source chess engine and a very very strong chess engine, superhuman chess engine, and when you play when you can set Stockfish to play at a certain level, and that is known as skill level. So here we are configuring Stockfish engine to play at level 0. Level 0 is the smallest level, and the largest level is level 20, where Stockfish doesn't make any mistake as far as it can tell. So now what is the so level 0 is the weakest, 1, 2 and so on, level 20 is the strongest. What is the difference between these two levels? And the difference is this. This is let it come up. My computer is a little bit overloaded because it is playing these games also in parallel. So what happens is that when you choose a certain skill level, it picks the suboptimal move, some suboptimal move at depth 1 plus skill level. So when we have made a skill level 0, it will do a very very shallow search. Not really. It will do full search, but it will pick a suboptimal move at depth 1 only. So more is your level, it will make the mistake far deeper in the tree, and therefore it will be a stronger engine. And what this table gives us a rough correspondence, rough ELO ratings of various Stockfish levels. So as you can see, Stockfish level 0's rating is around 1350. So if we can defeat Stockfish 0, it means we are more than 1350. So that is good. Maybe we are at like 1400, 1500. We'll need to play against other Stockfish levels as well. When I had done this exercise earlier, just a few weeks ago, before when I was not making this video, then my Stockfish 0 versus my engine, they were like neck to neck. And so I thought that maybe we are at level 1300 to 1350. But now when in this video, as a part of making this video, I just did all the retraining again. It's defeating Stockfish level 0 like all the time. So we are doing great. I'm aware of some subtle differences between my last approach and this approach, and I did not think that it will matter so much, but it did. Okay, so this is one thing. So nextly, let's just for the fun of it, let's analyze one of the games of Stockfish versus our engine. So let's go to leechess.org. Leechess is a great website, and what we will do is we'll do import a game, and then we will we have here matchgames.pgn. Huh? So let's observe the content of matchgames.pgn. Maybe let's pick up the first game, and we will copy from here to here and paste it right here. Hopefully it will work. Let's see, let's see. Yes. So white, we are playing white. Engine is playing white, and Stockfish level 0 is playing black. It doesn't show that, huh? NN versus Stockfish. It should show ideally NN here and Stockfish on the black side. Anyway, and this thing we will keep it on. Well, let's turn it off. Let's not bias ourselves, huh? And yeah, let's see what moves have been made by the players. D4, C6. Yeah, note that it is making very reasonable looking moves. D4, E4, NF3, very, very reasonable. While it is black who is making like all not that good, not that good moves. All right, it castles, great. It has understood. Now, yeah, there is no imminent danger. It still brings rook e1, fine. All right. Okay, okay. Yeah, black is clearly not playing that well. That is quite clear. We are attacking the queen, but the black decides to give away its queen. The queen is under attack, but Stockfish doesn't gather that, and we take the queen. Once you have taken the queen, then the game is nearly over. Again, black plays knight x f2, which looks like a poor move. I can just recapture with the king. So Stockfish is making too many mistakes. It captures the rook, it captures the bishop, and we take back the bishop. I would have liked that we took back the bishop by queen, so that to avoid creating the isolated pawns, but we are way ahead in the game anyway. All right, bishop comes out. Queen is slightly attacking. Actually, yeah, it's almost threatening mate in one. Although, yeah, it is no, not really mate in one, but close to that. It's pretty attacking move. Good. This is good by black, and this is and white makes q h6, which again is very profound. It's very profound in the sense we never told anything about what is queen, what is knight to the engine. It is still sensing that queen remaining here is disadvantageous for it. All right. Okay, it attacks the bishop, it saves the bishop. All right, brings out the bishop, brings out the knight again. I would say it's suboptimal move. Knight a6, why not knight knight a3, why not knight c3. Pawn, okay. Now it brings its rook here, and its queen on g7, threatening queen x f7, which will be troublesome for black, but black castles, great. It moves rac1. I would have rather taken r queen x f7, but anyway. Okay, this is good one. This, okay, this again, now Stockfish again makes a mistake. I can simply take back queen. I can simply take the bishop from queen, and that is what it does. So what I see is that Stockfish 0 is clearly not playing well, while Neural Net is playing all reasonable moves. It's not a very strong engine, just a 3-ply serve, just a simple 10 million parameter model, but it's making reasonable moves. Let's quickly go through it and go through the game. Yeah, maybe just a few moves. Okay. Attacking the rook. Will I take back the rook? Yes, I took that rook. Great. Yeah. So again, we are playing a very, very reasonable game. Again, a very reasonable move. Take back the knight. Take back the rook, and now it should be close to finish. we should have taken queen x c8, and it should be the end of the game. But yeah, so this is but it just does something random. This is a weak point of our engine, which deserves some mention, and that is that our neural net doesn't know mate in one, mate in two, anything. Actually, our neural net doesn't even know what are valid moves. It only looks at the position and just gives out an evaluation. Maybe sometime mate in 1 or mate in 2 has implicitly gotten encoded in the valuation because its eval is very very high. But note that neural engine has doesn't know about the rules of the game, doesn't know about concept of mate. It only knows that this is the position and this is its evaluation. So anything related to mate in 1, mate in 2, for example, this is a clear mate in few moves. You take your now it is not the engine, but I am moving it. You take your king here, and then you is it a mate? It's a mate. It's a mate. It's a mate in 1, but we have missed mate in 1. Actually, I'm a little surprised by missed mate in 1 because we are doing a 3-ply search. How can we 3-ply search should consider mate in 1? Okay, anyway, let's go ahead. And now, since computer will take the neural net will take all the advantage, but it doesn't know how to mate, and it is just passing its time. And sometimes I worry that the game in the end will get drawn. Yeah, you see here the black guy is making some good progress. It's took the bishop and then took the knight, and took the bishop and then took the rook, and we are just passing away our time because we don't know how to play the game. We don't, and finally somehow by maybe yeah, finally somehow we reached by chance a mate in 1 position and we found it. So as you can see, we are playing reasonable moves. This engine is playing reasonable moves in the opening, reasonable moves in the middle game, but when it has got a lot of advantage, it doesn't know how to convert it to the victory. It doesn't have that concept, and so maybe we will in future volumes we will train on those lines. Okay, so that was one pretty. I'm quite impressed by the engine that to reach this level of chess, it needs, if you are beginning, it needs at least 6 months to a year. Even if you are a bright person, it needs at least 6 months to a year to reach this level. While for us, we started coding up this engine yesterday or day before yesterday, and in that much time, and we started coding up day before yesterday and started training yesterday night, and in 12 hours we are at this level, with very very minimal compute. Really hardly any money has gone in this training. All right, now next what we will do is we will evaluate. We know that only around 50% of the times its evaluation is within a small range around the actual evaluation, and around 50% of the time our stockfish eval is way out of the window. You might remember this thing, that we are tracking within 1 accuracy. We are tracking within 1 accuracy, so it is around 55% in the best model. So around 40 other 45% time our model's evaluation is very very bad, and we would like to just observe manually some positions where the evaluation is good and where the evaluation is bad, just to get some intuition, and that will be the final part. So now what I will do is I will go ahead and do this game will continue. We will exit from here. The game is being played here, or rather let me do this. Yeah, let me just push. Let me control C this game. I'm quite convinced. We have won 5 out of 5 games. We are clearly better than Stockfish level 0, and even manually when we saw clearly we were outperforming Stockfish 0 very very clearly. So now what we will do is we will say, please create uh, a file which outputs, which reads fen and stockfish eval from what was our file, testdata.csv, and creates another file which contains fen stockfish eval nn eval, where nn eval is the eval of the position got from our model. Our model is what was that file? This thing, chess model epoch 063 .pt. All right. So we will create this data, and then we will see where the two descriptions, where the two evaluations are very, very different. So I will now pause this video, and when the evals are ready, I will be back. Okay, so I found out for each of the 360,000 test validation positions, what is the stockfish eval, that is the correct eval. Stockfish is our source of truth for now. And what is our neural engines eval. And so we found this out for all 360,000 positions. Let's look at how that file looks like. It looks like this. There is the position, the fen of the position, the stockfish eval, and the neural net eval. And now what I would want to do is, I would want to find out those positions where the position is clearly in favor of either black or white, but our model thinks that it is roughly equal. So let's do it like this. We will say cat test data with nn eval. We will run a awk script. We will say, we will separate by comma, and we will say so we want those positions where $2 is very big. So, and $2 can be big in any direction. So I should say absolute value of $2 is, let's say, bigger than 5 or bigger than 10. But I don't know how to take absolute value, so I will just take a square and I will say bigger than 100. So now it will filter out those positions where stockfish eval is bigger than 10 or lesser than -10. But I want that my eval should be less than 1. So square of my eval is also less than 1. So my program is saying its position is roughly equal, whereas clearly one of the sides is winning. So let's find some such positions. So yeah, so for instance, there is this position where actually the eval is 100, but my model says it's roughly equal. And eval 100 means it's some mate in 1 or mate in 2 type of situation. So let's have a look at this position. I will open Leeches, which is like God's gift to mankind, really. Tools, analysis board, and let's see what the position is. This is black to move. Black, this is black to move, correct. Yeah, white has given check and this is black to move. And the stockfish correctly thinks that actually white is winning, because black will prevent, the only way black can prevent check in many ways. One of the ways is, let's say, this one, and in that case he gets checkmated. White gets checkmated, or black can prevent check like this, in which case again it soon gets checkmated. So in truth, this position is winning for black, and that is why Stockfish eval is sorry, this position is winning for white, and that is why Stockfish eval is 100. But our model thinks, well, our model thinks the position is roughly equal. In fact, black has an extra knight. In fact, black has an extra rook, so maybe black is winning. So our model gives it an evaluation of minus 0.44, slight advantage for black, whereas it is actually white which is winning. So the reason is, as we know, the model really doesn't know the rules of the game. It doesn't know this mate in one, mate in two type of things. It just knows this is the position. It doesn't even know what is the valid move. So clearly, model doesn't do a good job there. Now let's take a position which is a different kind of position. Where let's see if there is a different kind of scenario which exists, where the reality is that the position is evenly balanced. $2 into $2 is less than 1. So $2 is between -1 and +1. But our model thinks that, dude, one of you is really winning. Huh? So let's say bigger than, I don't know, 10. Let me try with 100. There are a few positions which are actually equal, but our model thinks that one side is winning. Let's see this position. The position is dead draw, 0.0. It's black to move. It's black to move. The position is drawn, but our model thinks that black is hugely winning. Okay. And we can understand, a human may also think that black is winning, but yeah, if you know end game a little, then yeah, you go here, you pick your queen, and I pick my queen, and nobody wins really. So, but our model thought that it was black which was winning, and we can sort of give the benefit of doubt to our model. Yeah, let's pick one more position which is roughly equal, but our model thinks that the position is one side is winning. Let's see what is this position. Is this also an end game position? All right, here the position is equal, but the model says that black is winning, and it is black to move. I don't know why model says black is winning. Maybe actually just a minute. Yeah, you may be excused for thinking that it is good for black, because black has quite a few strong moves. It can give check, and if you go like here, then black is indeed winning. The thing is that you can just draw. Black has just found a perpetual draw position. That is why it is winning. Otherwise, black would have won. White has just found a perpetual draw kind of thing. Otherwise, if you move the wrong way, then black will win. So once again, our model is not really bad. It is not making silly mistakes. It is pretty impressive. Okay. All right. Now let's go on to the next part, where let's discuss a little bit about. Let me turn on the slideshow. Turn it on, man. It takes a whole lot of time to turn on the slideshow. Okay, all right. So let's do the recap and the next steps. Recap. We built a 10 million parameter neural network made up of convolutional layers and ResNet layers. We complemented it with 3-ply search, and we got an ELO strength of 1300 to 1400 within 12 hours of training on an A10G GPU. I think like it's pretty good job for a small amount of effort. And I'm not really sure of the ELO strength. We were defeating 1350 Stockfish very easily, so maybe our level is a little bit higher. And the next steps are that currently the model is totally not aware of valid moves. It has just made some sense, just figured out some patterns, figured out which position is advantageous, which is not, and doesn't know about valid moves. And that is one reason why you see some some errors in its valuations, lots of errors in its valuations. Then another thing that I was thinking was that can we have chess specific convolutions? Right now we are using that 3x3 convolution networks, which actually come from image processing kind of things, but here it's not really an image. Maybe you can have some bishop convolutions and rook convolutions and knight convolutions, and that way the model can better understand how things, what things are. Because right now we have not told the model that bishop moves this way or rook moves that way. Then maybe we can do a smarter search than 3-ply search in the and actually maybe there is a bug also, because in our analysis we found that once our program missed a mate in 1. Mate in 1 was not to be missed with 3-ply search. Another thing is my computer is a little slow. Another thing is that we can do is different networks for opening, middle game, end game. Maybe that is a possibility, particularly for end game. End game is if you know how to play chess, you would realize end game is a different, it feels totally different. So maybe we train a different network for end game. You see, our model missed in that pawn end game. Any grandmaster, not even grandmaster, even I will tell that it's a drawn move, it's a drawn position, but the model couldn't, because it is not specifically trained on end games. And lastly, while my motivation behind creating the chess engine was to learn neural network and reinforcement learning, there is no reinforcement learning here. We are just doing a 3-ply search. For now, I want to continue on the neural network side for some more time before we get on to reinforcement learning as well. But finally, we have to, that is the agenda, we have to understand reinforcement learning also through this vehicle of making chess engine. Alright, so we are at the end of this video. Let me see if I can turn my face big. No, I'm not able to turn my face big. Yeah. Anyway, I enjoyed making this video one very much. I will share the code. I will upload it on GitHub, put it in the YouTube link somewhere. And feel free to ask any questions in the comment whenever I am able to upload the video. And in case you would like to mail me, my email address is thevivekpandey@gmail.com. Yeah, so you can email me also if you have some questions to ask. And also those of you who are who know a little bit more about how to create chess engines, if you want to guide me, I'm going to spend some more months doing this. So if you want to tell me how to proceed, some obvious mistakes that I may be doing, then please feel free. Have a happy 2026 has just started. Have a happy 2026 to all of you. And thank you very much. Bye-bye.